All right, so this is part two of the chapter two lecture on metallurgists and careers in the metal industry. Just as a quick review here, what we're talking about is we're taking different compositions of elements, melting them together to at different percentages. We're using different processes like forging, rolling, casting to basically shape that molten material and give it a certain type of microstructure based on the process that's being used. And of course, then we apply other techniques in that to give us the desired properties that we are looking for out of that base material. All right, so here's some examples of metallurgy that we would need to use and kind of solve some of these metal related problems that we're going to run into. So the idea here, of course, is to get better metal parts. So learn the best metal for different applications. What's that mean? Well, if you've got a drive shaft, what are the metals that would work best for a drive shaft? If you're in a situation where you've got moving parts, like for example, in a camshaft or in a combustion engine that's going to be uh, handling high stress, high temperatures, what type of metals will work best under that environment. Um, what is the best method to actually produce that part? So we've got all sorts of different manufacturing processes that we can make it. Are we going to make it out of bar stock, round stock, square stock, plate, sheet? So all of these different types of goods. Certainly, we can make the part out of different types of raw material um, as we go through, but how will that starting material shape that we get from the uh, mills impact the actual part in its working performance? And then, of course, if those parts wear out faster or prematurely compared to what we originally thought they were going to last in the design times, what can we do to change that and improve those parts and have them last longer as well? So these are some of the types of things that we're talking about here when we're talking about examples of metallurgy and why you as a machinist or a welder or a quality personnel or engineer or any type of industrial technologist or industrial technology person would want to know and have a decent grasp of metallurgy. All right, so talking here, these are some examples. You can read more in the textbook about these as you go through. It talks about warped lawnmower blades. They form the lawnmower blade by stamping it out of a sheet metal and then kind of bending it. If you've taken the manufacturing processes class, you've learned a little bit about those particular processes as we go. They heat treat this. After one day, there's blades are rejected, and they've got a huge rejection rate. So come to find out, when they do some of their problem solving, trying to figure out what's going on, the mill producing the steel sheet had changed processing a little bit. And that processing change created additional stresses in the actual metal when it was rolled into sheet. So when it was heat treated, that relieves stresses and that caused warping. So you can kind of see here this process, this step-by-step procedure to get us the raw material, and then even the processes that we use to take that sheet metal good um, and get that into the final product that makes changes to the chemistry of the actual part and adds the stresses. We're constantly putting stress into parts no matter what manufacturing process that we're using. And then, of course, that metal reacts to that stress. So we need to kind of figure out how we can make changes to the process or develop the process in such a way that it minimizes the stress put on the part and keeps that part from failing. All right, so here the metallurgical solution that came upon this was to heat treat as received, elevate the temperature for 2 hours. Notice there's time element here, and then that relieves the internal stresses that were caused by rolling. So, all right. Here's a application down on the farm. So, metallurgical problem was to bend cultivator steel, control arm linkage for easier movement. So, of course, the metallurgical solution was to heat the end to be bent with the blowtorch. You get it to a red hot property, then you use the hammer and anvil to bend it for a better fit. Now, this is pretty common. So, those of you that are looking at doing any type of forging, of course, welders and even some machinists might have this application where we're going to heat parts up and heat steel to a certain temperature prior to bending that or shaping or forming it or even flattening it out from that point. And of course, the more experience you get, as depending on what type of steel that you're using when you are applying it to torch, you learn some of the different colors of that steel, whether it's an orange or a red or a yellow, and you kind of start to gauge a temperature of the steel based on the color that's being associated when it's glowing hot, and that kind of you use that experience of being able to tell a relationship between the color of the metal and the uh, temperature that it is at that particular cutter so that you know that it's ready to bend and process it. So, of course, then we're going to, in this case, reheat that linkage to bright yellow. They plunge it into a bucket of water so they can do a quick quench in that. And then, of course, file the scale off that's related and reheat one last time for stress relieving. Okay, so same thing here on an axle shaft. Usually any type of shaft, we want it to have a nice hard outer core and a fairly ductile inside core. So we want to keep that shaft from basically twisting apart or bending. So we got to increase the strength. So, and of course here it mentions conditions to keep costs down. They don't want to increase the diameter to make it stronger. They don't want to change the alloy. So what can we do in the case of that to increase the strength of that axle shaft? Well, here it talks about what I had just said, heat treating the outside. So we have a nice ductile unhardened core. We case harden or harden the outside to a certain depth. So that gives us a higher strength and wear resistance on the outside. Of course, typically the harder metal becomes, the more likely it might be to twist or break apart. That's why we want the inside core to stay softer and a little bit more ductile as we go. So these are types of applications that we're going to be running into as we go through and study metallurgy here this semester. So we talk about machining as a cutting tool. You know, the idea with any type of cutting tool, in order for us to cut a material, the material that we're using as the cutting tool has to be harder than the material we're cutting. And oftentimes those cut edges will lose their edge. So we might actually go to resharpen that tool. If we put too much heat into the metal when we're resharpening, we could actually be dulling it as well. So there's a process and an idea that you've got to know and understand as you're doing this. Of course, now today, in today's manufacturing world, oftentimes we're pretty much using inserts and just changing those inserts out. So when I was apprentice, we sharpened a lot of tool bits. Um, there is still in a small niche area for that, and there's still a market, especially for custom form ground tooling. But it's not quite as much as it used to be. So because of the insert technology that's there today, and again the wider range of different types of materials there as well to give us better cutting tools. So another way that we can do this, of course, you see here we're talking about cutting tool durability. And while as a machinist, we refer to different cutting tools in terms of the manufacturing processes that we're using. But a cutting tool isn't just talking about cutting tools and machining. So if you think about it, um, there are a lot of manufacturing processes that we take sheet good and more or less cut it down. Or so there are what's called slitter knives and cutter blades that also are used for cutting sheet metal or aluminum down to certain sizes. Uh, there may also be these type of tools. If you think about going over to Danville, to the Quaker Oats Company in Danville, they have a lot of what they refer to as slitter knives on their processing equipment, where they're making the Quaker Oat bars, and something is more or less slicing those bars into the shape that before it's going to packaging there too. So you have this idea of a cutting tool that needs to hold an edge. So, and that edge and the geometry of that edge is set, and the hardness of that edge has to be held and conformed to. And this is what we're talking about here in terms of improving those cutting tool durabilities. All right. In addition to performance, so sometimes the result that we want might just be aesthetics. So in this case, you're seeing an example of a high strength aluminum alloy. It's got to be strong and it's got to meet the desired strength capacity, but it also needs to look nice as well. So in this regard, they can use aluminum. It gets polished and it has a really, really nice look on custom cars. Okay. You get the idea here too. If you think about how washers are made, oftentimes these are just pressed or stamped out here. And this particular manufacturer had an entire shipment of these lock washers that were rejected because of fractures in the steel. So it weren't quite up to par with the quality standards that that particular manufacturer was looking for. So as they took a look, the product engineer and production supervisors this is the process that was made. So they stamp it from the sheet steel, it's twisted slightly to lock against the nut, and then it's electroplated. So we'll talk about different types of coatings and finishings and platings here in this class as well. The plant metallurgist talked about the likely cause of these brittle fractures was due to hydrogen embrittlement. We'll talk about what that is and what that means as well. And in this case, they kind of changed the process. So they had to do some corrective actions to the process to make sure that that didn't happen as well. And of course, for a company and to do something like this, you want to document all those changes there as well. So we talk about cooling fans. So to sake of time, I'm kind of going to allow you to go through. We talk about different things that can be done, ways that we can look at using some of these techniques in one industry, and how it is oftentimes shows up in another related industry, and how manufacturers can then use that to increase sales. So I'm going to stop this part 2 here and now, and when I come back, we'll discuss about one of my experiences on how one of the manufacturers that I used to work for figured out a way to kind of get more out of the material and the metals that they were using.